I wanted to share with you in about 10 minutes sort of my own view of where the future network might lie and what the drivers are that are going to get us there, and then spend maybe about 10 to 15 minutes trying to translate that into some ideas, not a complete set, but some ideas of what that might enable developers to really do and how that could change the kinds of tool sets that we have and can work with. So let me just talk a little bit about, is a gigabit enough? Because I think that one of the primary drivers that's going to change the way the network works is that we have this continuing move to higher and higher speeds. We've seen that continue. I see no reason to see that's going to stop. What I do see happening is that we've got uncompressed HDTV is already more than a gigabit. We've got medical images using DICOM format, about 6 gigabits if you're going to do 1080p and 120 hertz. That's certainly what the new medical imaging stuff is doing. The Red One camera you see the picture of over there, about 10 gigabits per second if you're going to go and take that signal uncompressed. And you saw that the 4K video things that were announced at the last CES show are going to run even higher rates than that. And there are already YouTube videos that you can get at 4K. If you have a 4K set, you can now watch YouTube videos at 4K. And 4K is not the end. People are looking at 8K, 16K, going beyond. Now, I think that we're going to have to get to some place where the Retina display in your living room has so many bits that the eye can't see anymore. But there's certainly some way to go, and there's certainly a lot of talk about Ultra HD. So can you really see a gigabit? Laptop screen, if you were trying to refresh it at sort of Retina display quality, about 4 gigabits. And if you had an even bigger one, a 15-inch Retina display, get the iPad bigger, that would require about 10 gigabits just to keep that display going at Retina quality if you're feeding that from another source with uncompressed video. Big data. I think that big data is clearly one of the things that's going to be a driver of bandwidth on the network. Let me not say any more about that in the interest of time. And of course, aggregation. When you get any number of people together doing some of these things, we're going to see continuing growth in the amount of bandwidth needed. So we'll need at least a gigabit. Maybe we should be talking about 10 gigabits, 100 gigabits. I like the 100 gigabit picture of the universe. I thought that was the right way to look at the universe. And it really made me wonder, what would happen if we had the terabit version of that picture? What would that really show us? I mean, if we could see that much more from the 100 gigabits, what would the terabit look like? So what will a gigabit stress? What's really going to kind of break economically if we're doing that? And I'd argue to you there's two things. One is internet routers, and the other is transporting things to distant clouds. So let me talk about both of those. Number one, the internet routers. Internet routers, at the time that they were first invented and first running, and I have to say I'm old enough that I remember that time, they were designed at the time to run at the blazingly fast speed of switching 5 packets per second. All right, you get 5 packets per second, that would be what we could go do. And what?
It's a human mail sorter.
It's almost a human mail sorter. It's a little bit faster than that, but it's still pretty good. And you could actually check a lot of things in that in the time that you had. You could go and check for this and that and the other thing and make some optimal decisions on a packet by packet basis because there was time to go do that. Well, if you're taking a look at a gigabit rate, we're looking at 75,000 packets per second and deciding again individually what to do with them because, and this is the technical part, the maximum packet size hasn't increased over that time really. There are some changes. There are some things called jumbo packets that some of my friends in the room know about. But we haven't changed it by orders of magnitude, which is what would be necessary to keep up with this. And the internet packet header has only gotten more complex. This is a picture of the IPv4 packet header. Some of these things are fixed places. Some of them have expandable options. And the amount of time and energy it takes to go through these and deal with all this stuff at the IP level is just getting bigger and bigger. Anyone know about how many RFCs apply to one IP packet? You know, it's over 4,000 RFCs, standards, that apply to how you have to deal with any one packet. So we're reaching a complexity crisis because we've got a very rich, very powerful, very capable IP packet, very capable and powerful, but we now have to switch so many of them per second that we're requiring lots of power and electrons and heat and silicon to go do it. It's growing faster than Moore's law, so we're losing the battle of being able to switch that much complexity that quickly. So the solution is very simple. We should, instead of switching packets, switch flows. Just have an entire flow of packets that changes and gets switched. Software-defined networking is one of the ways of doing that. It separates the control and the data planes so that you can optimize things end to end. You can slice off a lot of that IP overhead. And as the result, by taking out the complicated logic on a packet-by-packet basis, putting it into a controller on a flow-by-flow basis, you can reduce the cost of that thing that's actually executing the 75,000 packets per second by, you can reduce cost 80%, maybe 90%, because you can re-simplify what's going on. Those of you who know about CPUs know we did it once in CPUs. We called it RISC computing, reduced instruction set, make it simpler, faster, cheaper. And reduced instruction set is what's made, I don't have it on me right now, but my cell phone. The processor in that is a reduced instruction set computer. The simplification in the instruction set was what allowed that phone to get faster, smaller, and run on batteries. We're approaching the stage where this is going to happen to the network. So it's one of the big drivers that's happening. So the second thing that I think that is going to be stressed by the increasing speed is the transport to distant clouds. We have this cloud computing paradigm. We have to go and take things to clouds. They go and have very efficient data centers, probably locate them near rivers or other places where you can get inexpensive power. But taking gigabits to distant clouds can be expensive. And it can cost a provider in a typical American city, and I'm not talking about San Francisco or San Leandro, I'm talking about a typical American city. You know, think of your mules. Where's Mules? Yeah, in Middle Tennessee there someplace. You know, $5,000, even $8,000 per gigabit per month to be able to go and make that stuff work. And that can end up being quite expensive to get that data to and from the cloud. And there's actually a very simple solution to that. Move the cloud close to you. If the cloud is close to you, you can get rid of that cost that accrues from having that, trying to get the high bandwidth to and from the cloud. So keep the gigabits in your own neighborhood, folks. Have a neighborhood cloud. And there's another name for these neighborhood clouds. You can call them US Ignite racks, or you can call them, as Mark would call them, Genie racks. Genie racks are a great way of moving the cloud to you. And what you've done is you've changed the economics. Instead of having to pay somebody to get the all the way to some other cloud, you go and bring the cloud to you. Now, those of you who are in R&E networking, you're saying, what is this about? I get kind of free 100 gigabit backbone on the Internet 2 backbone to some other place. And all of that is true, but in the world that US Ignite lives in, where we've got lots of real communities and real places, the cost of that transport can be a real cost of transport. So getting things into neighborhood clouds is really pretty important. So an unencumbered gigabit of the future, or 10 gigabits, or 100 gigabits, or terabit, will probably want to use software-defined networking because you can go to that switching by flow and not by packet. And you can also use neighborhood clouds. But it's also very freeing, because if you're going to switch by flow, you can now talk directly to the controller and say, this is what I want my flow to do. It's the program everything that Mark talked about. It's the ability to go and get big flows managed separately that Eric talked about. It's that ability to go and say, we don't have to go and make each packet live by itself. We can go and make the flow live and do the important stuff. So that was the first 10 minutes. I've been on time, very good. All right, so now I wanted to talk a little bit about how this might apply to a number of things that we could go develop. And one of the things you've heard as a commonality from each of the speakers is that the internet might not be a single common big pipe anymore. Mark talked about slicing and virtual things. You remember his little colored arms coming out of his cloud. And we had Shahzad talking about disaggregation, being able to make that work. And we had Eric talking about how the large flows, your green graph, was handled separately in order to go and make that work better. And I'm going to argue to you that I think that economics is also going to drive this ability to have sort of multiple internets, multiple flows. And I'm going to pick for my example a home. So here's my home. And I'm going to argue that there is a need for not just one internet connection into the home in one of our communities, one of the US Ignite communities, but probably multiple internets or slices or disaggregations or the ability to go and have special treatment into that home. Now, I do want to start off with the ordinary internet because we're going to keep that. I'm not trying to get rid of it. Still have the ordinary internet. And I probably pay for that in the usual way, right? I go and I write a check for, I don't know, $50, $70 a month for whatever I want to have for my ordinary internet service. But I may also want to have some telehealth video. This is with my doctor. It's going to allow my doctor to make a home health call. There's two people right there who are all about this and will tell you what they're doing to try to make some of this happen. But I think of this as a dynamic flow that gets created for 15 minutes for that purpose. It might be much bigger than my normal ordinary internet. I might be paying for only 20 megabits of ordinary internet, but this might be 200 megabits that I'm using for the telehealth video. And maybe my healthcare provider pays for this. Maybe it's billed in a different way. Now, is this delivered over a separate physical pipe? Of course not. You know, remember what Shahzad talked about. This could be another layer on top of that physical pipe, but we'll think of it and we'll bill for it and we'll keep it maybe HIPAA compliant for a different purpose. Or perhaps community Wi-Fi. It strikes me that if you go down any residential street at any given time, you have at least 10 Wi-Fi signals in range, right? If I needed to access some neighbor's Wi-Fi for an important public safety purpose, because I see an accident happening, because I see a fire, maybe I should be able to use that other Wi-Fi just for that community access purpose. Well, that's an interesting thing to do. We could go and say there's an extra pipe that maybe is part of my taxes that comes into my home only when needed. It's dynamic, only when somebody sees a fire or when somebody sees an accident, and can be used by anybody, but only for a specific purpose, only for reporting that accident. You can't watch Netflix over this channel. It's a 911 pipe, right? So, you know, think about this as doesn't permit any other applications over this pipe because it's a separate slice, it's a separate thing that does only that. And maybe there's some interactive online education that, again, might be video-based or it might be edu-gaming based. So it might be a multiplayer educational game where they're going and constructing a model of an ecosystem. And they're playing Ecosystem City and trying to see if they can get a proper set of diversity into their ecosystem to go and have the plants and animals live together harmoniously. You know, it's a great kind of experiment to be able to run. And maybe, Bill, there's some home dialysis going on here. And we need very reliable communications. So this kind of looks like there's two pipes going in at the same time, but there's only two virtual pipes. I realize if they dig up the backhoe for that one house, it'll probably go offline. But the basic idea is that this connection is unlike the others in that it's designed to be very reliable, and the kind of service it gets is this very reliable service. So what we see here in this kind of model is that the application defines the virtual network. It can be billed to somebody else. It can have different characteristics. Some of these could have very little buffering and be real time. Some of them could have deep buffering and transport large amounts of data. Each virtual network could live somewhat differently. Some could be HIPAA compliant, some might not be HIPAA compliant. They could all live on the same physical network if we're routing things by flow, such as OpenFlow does, or VLANs do. I'm not saying it has to be OpenFlow, but if we can do it by individual kind of network, I think that the network of the future is going to allow those kinds of things. I had a couple of slides here I'm not really going to go through that talked about each of those separately, but there you can see the accident happening and the community Wi-Fi being able to report that from my home cell phone, or from the cell phone I'm carrying. This is the low-cost, low-quality video versus the high-priced, high-quality video. And this conundrum has now been broken by the notion that we could use additional bandwidth instead of either high-cost compression chips in order to have, in this case, an interactive online education experience at high quality and low cost. At least these guys and maybe some others in the room can tell you about how that's done. They can do it much better than I can. There's the dialysis machine bill that the person is on. So those are some of the things that could be application-defined network characteristics that your application could ask for. What is the API that you can use today to say, give me a network connection of this speed and this reliability and so forth? I think we have this afternoon and tomorrow morning to talk about some of those things and how that might be brought into place. What else could you do? Well, in addition to some of those things, one of my favorites is the notion that if you have some of this local cloud computing, you know, this is your US Ignite rack or Genie rack or local cloud, and it's got very low cost access to the local area, you can stream big bandwidth to, in this case, this is I'm not sure what it is, maybe it's an iPad mini, that is looking at an AutoCAD structure with some complication. And as you know, you can go and take these things, and as you rotate them, the little gyroscopes in there could send back signals that say, change the viewpoint I'm getting. And you could go and take the structure, and you can imagine kind of walking around it, carrying your tablet, and seeing the view change as you walk. And in order to do that, the device is not capable of, in itself, being able to re-render that based on the structure in that time period, but with big enough bandwidth back to a server rack, you could do that. You could actually make that happen. And in fact, this is also the technology behind, as Mark pointed out in the first speech, some of the Prasad Kaliam work on the virtual desktop. Yeah, I like to think of it as the virtual handheld window into a simulation or something else that's going on. So this is another kind of application, I think, that the new networking is going to really permit and make good things happen. And here's an edu-gaming, multiple player edu-game. I think actually I outlined one for you in words that was sort of just as good as that. So what tools do you have to already be able to make some of these things happen? If you want something that's programmable, which we heard about from Mark, and real time and dynamic and gigabit and low latency and on demand, we want these things to happen. How can we do them? You have a couple of choices for what you can actually do easily today. One is that there are these things, you can get switches and routers and networking from a number of vendors that either have proprietary and or open standard APIs that permit many of the things that we've all been talking about this morning to actually go work today. Some of the APIs that are proprietary are quite powerful. I think there's growing power in the OpenFlow and the other open APIs that are available. You can just do that in your lab. Second thing you can do is if you'd like something that is more than just can fit in your lab, you can talk to Mark, and there's a Genie mesoscale test bed that allows you to go and program most everything on a fairly large scale. That's another option that you've got. But let's say you want to have just a small scale. Well, what I've done is I've got a Netgear N600. I've flashed it with the OpenWRT software, and I have an OpenFlow capable device in my home that I'm using to keep all my home flows separate. So I had a problem where I was running my television using silicon dust boxes talking to my Windows Media Center, and that was interfering with my voice over IP telephony, and I needed to separate those flows. So I got my N600 to go and put those on separate flows, keep them distinct from each other so that the video doesn't go and get in the way of the voice over IP. And I did that by inserting a few rules on port 6677, which is the OpenFlow programming port, on the N600 router. So you can do that too. You can even get 2 or 3 or 4 of these things. They only cost $100 and some each, and you can do it in the small. So there's lots of options for ways that you can take and program the network to do interesting things. And by the way, the OpenWRT is based on all open source software, so if you'd like to insert a new module, you can go do it. Yet another way is how many folks have Linux v3 installed someplace? Not too many, a couple of folks. Open vSwitch is a standard part of that Linux 3.3 distribution. So you can just get some standard Linux boxes. You've got Open vSwitch in there. The source code is open. If you don't like or you think that OpenFlow itself doesn't do enough to allow you to program what you'd like to do to make your application happen, you can go make it happen just by programming your Linux 3.3 box. So there's lots of choices for being able to go and modify and make all this stuff happen. So with that, thank you very much. I really appreciate your time and attention this morning.